Alright, hell yeah. So we have dynamics, and man, I'm kind of striking out because what I'm trying to do is do this like a textbook example and just kind of work my way through it. You know what I mean? And we don't even have to read the problem. Well, I guess we have to kind of read the question they're wanting. So this thing is going to be rotating, and it's going to be rotating at 3 radians per second. Again, I mean, not again, I've been doing this video like 5 times, but a circle is 6 radians. So every 60 degrees is about 1 radian. So it's going to be spinning about this fast. So we got 1, 2, 3, 4. See how I'm going 3 radians in a second? You know what I mean? So 1, 2, 3. So that's how fast it's spinning. Now it is spinning this way, and they just want to know, like, at this point, at 30 degrees, while it's spinning like that, what's a few things. Like, what's the, like, how much is this bar, like, rotating that way? You know what I mean? Is it going to be rotating the same speed? Now, if this slider was, if this point C was right in line with this point A horizontally, and these two bars were the same, it would be 5 inches, 5 inches, then, hey, you could imagine that when this moves this way, it's going to mirror, this angle is going to mirror that angle. So that would be one scenario where you're just like, oh, hell yeah. If this is moving 3 radians per second, this is moving 3 radians per second. Now, this is one of those videos where it's just like, you know, do I spend hours like diving into everything, or just saying, you know what I mean? Because the other aspect, we can just do this visually. It's kind of interesting just using words. If this is hella long, you know what I mean? So we're going to have this 5-inch bar right here, and this bar is just going to be hella long. So let's say this does move from like 30 to 0. You know what I mean? Did this bar like move at all? You know, it didn't move very much at all. So that's one scenario where this bar like hardly has any angular speed. If the longer this bar gets, the less angular speed it will have. Like if this is going from here to there, and we already said, you know what I mean? Hey, it's going from like 60, well, anyway, you know what I mean? So you can just see that the angular speed here is going to be like whatever it is, but if this is really long, it's going to be a little bit less. And then I guess the third scenario is if this bar right here was hella short, and then here's your slider up at C. So if this thing is just like right here moving back and forth, hey, a small change here is going to make this go flat real fast. So, you know, a small change in angle makes this bar go from 45 or like 60 to like 0. You know what I mean? So that would be a very fast angular speed. So at that moment, you'd have fast angular speed. All right, so it's kind of interesting how they solve this problem. A prereq for this is knowing, I guess I'm going to draw one more thing. Let's say you just have any triangle that has, you know, just different angles, like no right angles, you know what I mean? So what you do is you just do that and then make a right angle. So now you have 2 triangles. And these 2 triangles, well, hey, this has a theta, this has a beta, and we know we have a common side right here. So even though this is the top, this would be point B, even though this doesn't look like a triangle, well, it kind of is, and it doesn't really matter. You can make usually what you'll do is you'll do probably this, you know, make a triangle right here and then a triangle right there, and even though it doesn't look like that, well, hell yeah, you do have a square right here, so you have everything you need. Now, what they're kind of doing is they're saying, hey, let's just find this point B, and you could say this point B is like, well, let's see how far over it is. Well, to get how far over it is, the only dimension from here to there that I have is on AB. It's 5 inches, but it's that way. So what do we know if we know this angle? What's this dimension right here? And just visually, you know, if this is 5 up this way, what the hell is this? This almost looks like 5. It's not quite. And but it's going to be like 4.4, you know what I mean? Even if I break out my calculator and I go 5 times 0.866, which is what it is, it's 4.3, you know what I mean? So, so how do we do that? Well, we know this angle, and we know that this is the opposite of this angle, you know what I mean? I do the sun is shining on the sine. So we know that this is the sine part and this is the cosine part. So, and we know that the hypotenuse is always the bigger number. I can't stress that enough. So, and we know that sines and cosines are always smaller numbers. They're like basically fractions between 0 and 1. Like decimals, like parts of a whole. You take any sine and cosine, multiply it by 100, that's the percentage of this hypotenuse. So, you know what I mean? So when we take cosine of this angle, we get adjacent over hypotenuse, and that's going to be give you 0.866 if this is 30. So you're going to get 86.6% of 5. And so we can do cosine of 30, that's going to be 0.866. Anyway, so that's what they get right here. So you're going to take the bigger number and then multiply it by a fraction. And so to get this distance. Cool. So we have 5 cosine theta. And this is just the generic. We know that theta is going to be 30, but you kind of just want a generic equation. All right, hell yeah. And so what the hell we trying to do? We're trying to get where point B is. Okay, sweet. So point B is using this thing is going to be 5 cosine of theta. Cool. Now how do we get point B using this thing? You know what I mean? Well, we say that it's oh, this is kind of, well, no, yeah, it's not bumming me out, but okay. Yeah, it's just kind of interesting. No, this is probably the trickiest part. It's like, what are you equating? You know what I mean? And what they're trying to do is they literally are equating the position of B. All right, hell yeah. And I think the hardest part about these problems is like, well, how did they get this term x of c? So what I would do is even just using distances, like, hey, these distances are vectors, you know what I mean? So this distance, like right here, is bx. This distance right here is b, well, that might not be true. This distance right here, this distance is by. So to get to this point, we're going to go over bx, up by. Same thing right here. This distance is going to be cx, and then we don't have to go any height because there's no height in y. So cy is equal to 0. Okay, hell yeah. All right, so yeah, that kind of cleared things up. Probably hella confused things, but so now what we have. So if we start with the more complicated one, we're going to say, hey, if we take cx minus the 8 cosine beta, we get to this x value of b. So sweet. So we have cx minus 8 cosine beta. Cool. That's going to be, this is equal to bx. Okay, hell yeah. That's that distance. Now we can also see that bx is just, that's why I probably shouldn't have drawn bx right here. Because if we're just trying to get the generic, you know, if this is point B, we have a bx and a by. But we also see that that's just going to be 5 cosine theta. So we have bx is equal to 5 cosine theta. So these are the two things that were equalized. You know, like, hey, those two things are equal. That's how we get this equation. Cool. 5 cosine theta is equal to cx, that's what I'm calling this, minus 8 cosine beta. Okay, hell yeah. And then just like you would... and then you can do it in the y direction. So we can say that yeah, and this is what you want to do. You want to use by. So let's do that. So we're going to go by. Which one should we do first? Let's do this one over here. It's going to be 8 sine beta. So this is the sun is shining. This is the sine component. Obviously, this is the larger number. This number is a little bit shorter, and so we're taking the larger number 8 times sine of beta. Okay, hell yeah. And so we're going to take 8 sine beta. That's going to be by. Over here, we can take 5 sine theta to get this part, but the total by is plus 4. So to get all the way up here, we're going to we're going to go 4 plus 5 sine theta. So by is 4 plus 5 sine theta. And that's what we have here. We got 4 plus 5 sine theta is equal to 8 sine beta. Okay, hell yeah. Now we got our two equations. And, you know, you don't have to do this right now at all. You know what I mean? This was kind of an interesting step in the book. They took the liberty just to say, hey, if theta is 30 degrees, well, sweet. You know what I mean? We know that theta is 30. We know what beta is. You know what I mean? So we know when this is 30, hey, this looks like about 60. You know, maybe 45 to 50 to 60. You know what I mean? Maybe it's... So anyway, and then they do that and we get 54.34. So cool, we solve for beta. You didn't have to do that. Alright, so this is the trickiest part. And this is where I just wouldn't do it this way, but this is why I'm terrible at differentiating. I just don't. I think it's like a magic trick, you know what I mean? Because you have all the rules for differentiation, so when you do differentiate, everything just magically works out. And but anyway, so I did learn some things from this problem. So what we're going to do is we're going to, we're going to differentiate one of these equations. Oh, even just right there is just like, well, why didn't we differentiate A? We do that in part 2. Part 2 says we differentiate equation A. So that's kind of interesting. So part 1 says, hey, we just want to know the change in angle of beta. Cool. And so from the differentiation, we need to have beta dot, or change in beta divided by change in time, or d beta dt. That's kind of what we're shooting for. All these things are the same, so we just need to differentiate. Now, if we, yeah, and I guess that just, we've got these two equations to differentiate. Obviously, you would differentiate this one, because if you do, then you'll be able to, isolate beta. And kind of looking ahead, it's just kind of interesting. We do angular speed as omega, and this is 3 radians per second. Now, this is for my brother. My brother would never do this. He just got too hooked into like, nah, I wouldn't do this omega. I would do this as what would he do it? Oh, yeah, theta dot. You know what I mean? So this is going to be theta dot. Sweet. Or that's going to be d theta dt. D theta dt, theta dot is omega, and it's going to be omega of this angle theta. What does that even make sense? All right, hell yeah. Just like this could have an angular, I mean, it's the angular speed of bar AB, which is associated with this angle theta. Just like the angular speed of bar BC is going to be associated with angle, it's going to be the change in beta change in time. dB dt or b dot. Okay, hell yeah. Okay, so when we differentiate this, use our rules of differentiation. 4 differentiated goes to differentiation of a constant is 0, so we got 0. And then we have sine of theta. Now this is one that I will take my time on because what's sine of, let's do this, just draw something. Sine of 0, we're going to throw a 0 in here. And anytime you're doing, I would get used to this. I would do a 1, 2, 3. And this is going to get you up to 90 degrees, and this is going to be 1. You know what I mean? And I would just stay on the positive side of things. So when sine is, and this is going to be in radians, you know what I mean? And the reason you would do, or it's like 30 degrees, but it's going to be, you're going to 90, you know what I mean? And so if we go back to our circle, this is 1 radian. Well, it looks like 90 is 1.5, so that's another good one to know. 90 degrees is about 1.5. It's 1.5, what is it, 1.51, well, it's 3.14 divided by 2. That's going to be 1.57. Sweet. So there you go. And when you divvy this up, it's just good to know that, hey, it basically looks, at 30 degrees you're going to get to half, and then at 60 degrees you're pretty much going to get all the way to 1. You're going to get to 86. I mean, so this is what I would do for sine, and then it kind of curves like that. Okay, so this is sine of theta. We're going to do cosine theta. Same thing, 1, 2, 3. Draw our 1, and cosine of 0 is 1, and now it goes the other direction. You know what I mean? It actually kind of starts off like this and then goes to there. So it's just the mirror image. And what we notice is that, like right here, this part is like the change in slope is approximately 1. The slope is, like right here, is going to be -1. The slope initially right here is +1. Okay, hell yeah. So when we differentiate, what is differentiation? It's finding the rate of change, or it's the slope. It's a change in, what is differentiation? Oh yeah, hell yeah. So differentiation for like sine theta. How do you even write this? You would say the d sine theta d theta. This is how you write differentiation. And what this says is that you stack them. And so this is going to be rise over run. You know what I mean? The function is sine theta, and then the x value is going to be your theta. You know what I mean? So if we're going to go at 30 degrees, this is 0.5 radians, 1 radian, 1.57 radian. You know what I mean? We got that. And so, and then at 30 degrees, we go up 0.5. So there you go. So we're going to go, so I would do the bottom first, even though it seems like you would want to talk about the top first. When we change theta by 0.5, sine of theta goes to 0.5. Okay, so that's going to be a slope of 1. You know, I mean, we changed this function from 0 to 0.5, and we changed our angle from 0 to 0.5 radians. Hell yeah. And so that's going to be a +1. And now I guess when we figure out the differentiation of sine theta, we know that it's going to be 1, but then up here towards the end, look at that, the slope is 0. So when going from here to here, hey, we changed our theta by maybe like at least like 0.2 radians, and our function sine of theta didn't change at all. You know what I mean? It's basically 1. You know, you get up there to like 0.995. You know what I mean? And then, you know, you change by 0.2 radians. That's a pretty big change. And look at this. It only changed, you know, 0.005. I think I got that right. Anyway, hell yeah. Alright, so that's craziness, because all that was just to say, hey, when I differentiate sine, you know what I mean, 5 sine theta. Well, the 5 can pull out here, so we got 5 d sine theta d theta. You know, the 5 is kind of like, who cares about it? It's just a multiplication of whatever we get. You know what I mean? So if we have, if we know that our slope is going to be 1, well, guess what? It says multiply that by 5. Okay, sweet. So now it doesn't mean the slope is 5. It just says, hey, whatever the slope was, then multiply it by 5 to make this equation. But yeah, that's the fascinating thing, is that I would want to do a ton of simple differentiation problems that like make more sense to me. You know, I just find it interesting that you can have an equation and be like, okay, we're gonna change when theta changes with time, like beta changes, and then this position C changes. It's kind of just that's fascinating to me. Now we're not differentiating this equation, we're differentiating this one. So hell yeah. So 5 sine theta. Oh, and then how do you get what's the differentiation of sine theta? Like, what is the function? Well, if you when you throw in at 0, when you have 0, the slope changes by 1. So you need an equation where if you throw in theta is 0, it gives you 1. Well, no duh, that's cosine. Cosine, when you throw in 0, does give you 1, and that is going to be this slope. See how that slope is right there? Okay, hell yeah. And now we're going to have to differentiate, and that's it. We're just differentiating sine, but we should go over when you differentiate cosine for part 2, what the hell does that mean? That means that, hey, look at this. So right off the bat, you're going to have almost no change. Okay, so what gives you, when you throw in theta is equal to 0, what gives you 0? Well, that's going to be sine of theta. Sine of 0 is 0, but it is going to go down a little bit, you know what I mean? With just a little bit of angle, you're going to have a slight down slope. So this is negative sine theta. That's how I memorize it. But anyway, that took way too long to get there. But that's going to be, it's just really good to go over what a derivative is. And then when you differentiate sine theta, you're not just looking in the book just to be like, okay, sine theta goes to cosine theta because it's just opposite. That'd be nonsense to memorize. You know what I mean? When you can just kind of learn visually what's happening. Okay, hell yeah. So when we differentiate this, we're going to have 5 cosine theta is equal to negative 8 cosine beta. But then the fascinating thing is, I never think about this. I have to look this one up. So when I go differentiation of sine theta d theta, this is going to give me cosine theta d theta. Is that right? Is this how it looks? Because that's kind of what they're showing. I'm going to look that one up right now because that's gonna mess with me. Holy hell. Okay, so I know what's going on here, and this is the crazy thing about textbooks, because like this is why you need a professor, but I don't know how you're going to learn, because the professor can't, the professor can lecture, but holy, that's it. You hardly have any hours that you can actually go in and talk to a professor being like, how the hell do you get this extra term? And, man, they should really show the differentiation part. And maybe they do in other things, but so we're going to go over this. Because it says you're differentiating with respect to time, and that's going to be the kicker, I think. So let's try this, because we're going to have we're going to differentiate this. We're going to differentiate 4 plus 5 sine theta. You know what I mean? And we could get the other thing anyway on that side. And then we're going to have dt. Okay. Oh, yeah, no duh. So you do need the chain rule. So the chain rule says, like, hey, I'm going to have, hopefully I'm doing this right. So you're going to have d of whatever, dt, but we can't do it. What we need to do is d of this function, d theta, because that is what the function has in it. And then we need to go d theta dt. You know what I mean? And then when you could easily just cross those out and then you're back to here. You know what I mean? But it's just fascinating that this happens all the time. And I don't even know if this is polar coordinates. That was the thing. That's why I kind of failed. Well, I never failed this class, but damn, I have figured out a way to get through it with the minimal effort. I just knew it was a weed out class, and I knew that from a civil engineering perspective, a lot of this stuff's not going to be moving. And so, yeah, I wasn't into mechanical engineering. But this is the stuff that I'm most fascinated about, because it's just like, well, why aren't they saying that you have to, like, even just right here, it's just like, well, yeah, differentiate using at least the chain rule. You know what I mean? Just write that in. That's crazy. Okay, but when we do have d theta dt, cool. Now we can differentiate with, because that's the thing, you're just thinking, oh, I'm just differentiating. No, you're not. The only way you're going to differentiate this is if you do differentiate with respect to this variable. And so, so over here, and it's going to be the same but opposite. You're going to have d8 sine beta dt. Well, you can't we don't have a t up here. You know what I mean? So now we're going to do this. We're going to do differentiation of 8 sine beta d beta. You know, we don't have a theta either. You know what I mean? So we're going to have to differentiate with this beta, and then d beta dt. Okay, hell yeah. So that was, I'm so glad I did this, and I'm sorry if these are, I don't know whether these videos are just junk, but man, the only way I'm going to get better is by doing this method, you know. And there's plenty of times where I've turned on the camera, have done like a full 30 minutes, and just, nah, this sucks. But this one's good. If I come to some pretty cool conclusions, and the cool thing is I try to learn on the fly, and so hell yeah. So now we're doing it. And so this is where, and we've already said that d beta dt is change in beta, change in t, or it's just beta dot. You know what I mean? So that's where that beta dot comes from. And also d theta dt is omega. So this is also omega. And again, the angular the change in beta with respect to time is the angular speed of bar BC. Those things, and I swear I got through this class. I didn't know like how things like actually the angular speed of a bar. Hell no. Like I passed this class without knowing that at all. So sweet. All right. So hell yeah. So those are synonymous, because there's a lot of things. It's like, hey, that's synonymous with that, and that. You know what I mean? Cool. Okay, so now we can just kind of do it in one step. That's where they get 5 cosine of theta, because up here you're gonna differentiate this whole thing with respect. You're gonna do d dt. Yeah, well, cool. There's not a t up here. There's not a t here. So we're gonna chain rule this with respect to theta, and we're going to chain rule this with respect to beta. That's where we get 5 cosine theta, but then we're going to have a d theta dt, which is theta dot. Then we're going to do this. This is going to be, now, why didn't this turn out to be, oh, and then my bad. I got too wrapped up in talking about sines and cosines, and then I just figured this was different. No, this is another sine, so it's just going to be 8 cosine beta. There's no negative here. Booyah. So 8 cosine beta, but you have a d beta dt, and change in beta with respect to time is angular speed. Now change in beta with respect to, oh no, yeah, I don't want to confuse anything else. There you go. So we did the chain rule. You have this d8 sine beta dt. You can't do that, so we have d8 sine beta d beta. Yeah, we can take the derivative of that. That's just going to be 8 sine, sorry, 8 cosine beta. Done taking the derivative, and then this is just going to be b dot. Hell yeah. Alright, so that's what we get here. And we know, you know what I mean, again, theta dot is d theta dt, which is omega of bar AB. Sweet. So we know the angular speed of bar AB is 3 radians. So we do know that theta dot is 3 radians per second at this angle 30. Sweet. So then we know that this is 30 degrees. This is going to be 3 radians per second. And then this is going to be 54.34. Hell yeah. And I won't get into too much of a hassle of making this negative, you know, because, oh man, it's they're showing that, hey, if this is the, you know, the origin of like 0 degrees, you know, 0 radians, then a positive angle is going to be this way. You know what I mean? It's going to be counterclockwise. But this thing is rotating, you know, kind of in the negative direction. So then when we do that, okay, let's throw it in -3. So you're going to have 5 cosine 38 divided by 8 cosine 54. Hell yeah. And then multiplied by -3. I'm not going to go over any tricks to do this mentally, but booyah, you're going to get -2.85 radians per second. And now, yeah, I guess, yeah, I mean, if we set up these equations, yeah, that's kind of cool. You know, if we set up these equations as such, the positives and negatives are going to give us the right value. So we've assessed that this thing is rotating in the negative angle. The angle is reducing on this theta, and when we throw that in, it says that this angle is reducing. You know what I mean? The only thing that's bizarre is it's not, this negative isn't associated with the same direction. So this is rotating, the angle is reducing, and that's going to be a clockwise direction. Now this angle is going to be reducing, but that's going to be a counterclockwise. So that's the only thing that doesn't match up. A negative right here is a clockwise. This negative, the angular speed of bar AB is -3 radians per second in the clockwise direction. And a negative radians per second is going to be in the counterclockwise direction. The negative just indicates that the angle is reducing. I think if you took your origin here to be 0 like you did here, and this to be your beta, now you can do that, and you can actually arrive at the same, you know, I think your equations are a little bit different. I never like to do that. I would rather have my angles between 0 and 90, so then I don't freak out, and you know what I mean. Yeah, it's going to be too much for my brain to figure out the trigonometry using that angle. Anyway, that's just me. I should challenge myself and figure out this height based on the angle being over here of beta. All right, hell yeah, we got to move on. But that was it. I mean, that was at least one part of the problem, is finding the angular speed. And we have an equation that says the angular speed of bar BC. So B dot, again, is dB dt, which is omega of bar BC. Those are synonymous, and here's the equation. 5 cosine theta, 8 cosine beta, and then what we want to do is there's a couple things here. The question says when theta is 30, hey, what's the speed? You know, and then we did a side thing figuring out beta. But what you can do is you can solve for beta over here and just say beta is inverse sine of 4 plus 5 sine theta, and then you could throw this equation in for beta right there. So then you have an equation for this angular speed just by inputting theta dot, you know what I mean, the speed of this bar and whatever angle, you know what I mean, because then it's just like, hey, you 2 inputs and you get the answer, because there's 3 things going on. We're gonna input this. This is kind of like and you could get if this thing did actually rotate around in a circle, like a motor does that really well, just a nice constant angular speed. You turn on a motor, it's going to go one speed. It's not going to go variable speed unless it has variable speed input. So hell yes, that's going to be our input on speed. And then we're going to, at whatever angle we're analyzing, could be anything between 0 and 360. For this problem, this is kind of constrained within a small window. So then that, so those are our 2 inputs, speed and angle, and obviously this angle beta, this equation could go right into there. All right, hell yeah. So if you did that, because what the next thing they want to know the acceleration of bar BC. So they want to know the angular acceleration of bar BC, which is the change in omega of bar BC, dt, which is the this is fascinating. It's the change in dB dt divided by dt. You know, it's the change in So that's interesting. It's the change d, or you could do it this way. This is fascinating. Just like writing these symbolically is kind of fascinating to me. So the angular acceleration of this bar BC is going to be the change in beta dt dt, which basically is saying, hey, we have the change in the change of beta dt divided by dt squared. So this is where you get d squared beta dt squared. Now this dt for sure is squared, but this indicates the second derivative, you know what I mean, of the position equation of just the angle beta as a function of time. We're taking the second derivative of that. Hell yeah. Alright, that's another aspect. I just said the angle beta with respect to time, and I think you could get an equation. I think you could get an equation for beta as a function of time, where you just have, you know, whatever nonsense and the variable t, where you input a time and you're going to get beta. You know what I mean? You're going to have an initial, like, hey, let's say at 30 degrees, that's going to be time 0, but then if this is your angular speed, yeah, you could come up with an equation for that. That's kind of interesting to me. Okay, hell yeah. So what we're going to do is we're just going to take the second, we're just going to differentiate. So we're going to have this equation. And what would I do? What did they do? I don't even know what they did. So, okay, hell yeah. So we're going to, we're going to take this equation, and then we're going to differentiate it again with respect to time. Now again, and this is fascinating, because now we have two things. We have a product of two things, and so then we have to take the first times the differentiation of the second. And that's where I was just like, hey, let's just run through this from a textbook standpoint. And this I will, because I'm just not super solid. Again, we have a constant 5, so we can just take that out of the derivative. But let's write this at least once. So we're going to have, we're going to differentiate this with respect to time. So we're going to have d, blah, 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 dt. But we don't have a t in here. So we're going to have to use the chain rule. So we're going to go d of this is in the, d of that function, d theta. Hell yeah, we got a theta in there. And then d theta dt. So sweet. And this d theta dt is just going to be theta dot. So we're going to have another one of those. All right, hell yeah. And we have a product of two different things, because we can take the derivative of theta dot dt. That's just the second derivative. You know what I mean? That's the derivative dt of d theta dt. You know what I mean? So that's how you write that. And hell yeah. So it's not d theta squared, but this d goes to this. It's going to be d squared theta. But yeah, see how you don't have a d theta out here? You know what I mean? So it's just those little things. That's why I hate differentiation, because no one explains that. And even though I just point it out, it doesn't mean I have a PhD in understanding why it's not d theta squared. You know what I mean? But I do like to write it as much as I can, because like the writing tells the story, and not too many people are going to spell it out for you. All right, hell yeah. So I'm still enjoying myself on this one, and then we got dt squared. You know what I mean? So it's the second derivative of theta, which is also theta double dot. You know what I mean? Which is also angular acceleration of this bar AB. You know what I mean? So there you go. Hell yeah. So that's where we get that. So we have the product. So it's the first times the derivative of the second. So we're going to have cosine theta times theta double dot. Is that what we have? Hell yeah. Cosine theta times theta double dot. Okay, now plus, so it's the first times the derivative of the second plus the second. So we're going to have theta dot times the derivative of the first. So what's the derivative of cosine? Let's go back to here. We're going to have a downward slope, but it's going to be something with 0. So it's going to be negative sine theta. So instead of the first times the derivative of the second plus the second times the derivative of the first, we did end up with a negative. So it's going to be cosine theta double dot minus sine theta, and then we're going to have, where did we get the squared here? Oh, this is going to mess with me. Oh yeah, no duh. Alright, hell yeah. So we're back, and this is amazing because, man, I'm learning on the fly, man. And no one taught me this in college, I swear. You know, maybe they did and I just wasn't paying attention. But holy Toledo. Okay, so we're doing it. So we're going to differentiate this with respect to time. So let's do it. So we're going to have, we're going to pull the 5 out, you know what I mean? And we can just get rid of it for now. We just know that after we do everything, we're going to multiply by 5. Cool, we got that part. But now we're going to differentiate with respect to time. So we have this, and then we have cosine theta, and then theta dot. But theta dot is d theta dt. So sweet. So now we're going to have d theta dt, and we still have a product. You know what I mean? We still have two different things. You could write it like this: cosine theta, box it in, and then d theta dt. So now we have a product of two different things, and then we're going to take the differentiation of that. And so when we do that, we're going to take the first times the differentiation of the second. Well, hell yeah, we can totally differentiate d dt of d theta dt. No chain rule required, because this already is a function of time. You know what I mean? It's oh man, and it's so weird how you get like just enough to be like, okay, I get it, but then just even saying that didn't make sense because it's still like a function of theta. But let's write this. So we have whatever theta is, you know what I mean? But yeah, that's right, because and then we're gonna change theta. But yeah, I don't want to get into it. And again, we could get an equation for theta as a function of time, maybe. But yeah, so I guess, but all this is just going to be theta double dot. Okay, sweet. So let's do this. Let's do this. So we got the first times the derivative of the second. So we have cosine theta times theta double dot. So I got that part done. And now the second. So we have d theta dt. So that's going to be plus the second. I'm just going to do, this is why I don't like textbooks, because I wouldn't do it in the order they do it. I would say, hey, this is going to be d theta, this is going to be theta dot times the derivative of cosine theta, which is negative sine. Whoa. And yeah, that's where I messed up. So we're going to have first times the derivative of the second, and we can take the derivative of this with respect to time, check mark. But then when we do the second times the derivative of the first, you can't take the derivative of cosine theta with respect to time. You have to use chain rule. So we're going to have, so when we take this second theta dot times the derivative of the first, we're going to have to do this, d theta of cosine theta d theta dt. You know what I mean? So did that spell it out enough? Because if we have d dt of this function, you know what I mean? Well, we can't do that. Yeah, and so let's do it the fast way. So we got this dt. We know this is a function of theta. So we're going to say, hey, this d theta dt. And then that works out. That's what we did. We had derivative of cosine theta d theta dt. Hell yeah. Alright, so can we just do that in one go? Let's do it again. So we have the first times the derivative of the second. That's going to be theta dot because it's dt. Plus the second. So that's going to be theta dot times the derivative of the first. We have to use the chain rule. So we're gonna come down here, and hell yeah, we can take the derivative of cosine theta. We just can't forget about this, and this is another theta dot. So we're gonna have negative sine theta, because that's the derivative of cosine. We just went over that. And then we're gonna have another theta dot. So this is kind of how I would write it, even though that they just do negative sine theta double dot. And that's booyah where they get that. So where are we at? Hell yeah, so we're just right down there. Whew, that took forever. And, well, I guess we're just right in here. You know, it's the same thing, though. All right, so now let's do this side and see if we can just kind of walk our way through it just using words. But even back to this one, multiply by 5, we get that. So we're going to, hey, let's just drop the 8 because we know we're going to multiply through. We're going to have the first times the derivative, and we're differentiating with respect to time. This is beta. This is d beta dt. So sweet. So first times the differentiation of the second. So this is going to be cosine beta double dot. That's what we get. And then we're going to get plus the second. So that's going to be our first beta dot. Times the differentiation with respect to time. We can't. We got to use chain rule. So we're going to differentiate with respect to beta, but then we have to multiply by d beta dt, which is another beta dot. So our beta dots are squared, and then differentiation of cosine beta is that negative slope, and then at 0 we need something where it's 1. No, what the hell? The cosine, the derivative of cosine theta. When we throw in 0, the slope here is 0. When we throw in, when we throw in theta is 0. Anyway, hell yeah. And then what equation when we throw in 0 gives us 0 for the slope? That's going to be sine. So and then it is downward sloping, so we have a negative sine theta. So sweet. Should we talk through that one again, just a lot faster? We're going to multiply by 8, but we're going to take the differentiation of this. We do have a product. We need to take the first times the differentiation of the second. So we're going to have cosine beta times beta double dot. Got it. And then plus the second, so we got that first beta dot. Times the differentiation with respect to time. We can't do that. We've got to use chain rule. D cosine beta, d beta, we can do that. But then we're also going to have a d beta dt, which is another beta dot. That's where you get the beta dot squared. And then when we differentiate with respect to beta, this is going to be a negative sine beta. Sweet. So we got negative sine beta. Beta dot squared. Multiplied by 8, we did it. Hell yeah. And then so, with nothing too crazy in here except maybe this acceleration. This is 0 though. That's the thing. I haven't even looked at, where they got the problem, but hell yeah. Because we're saying that AB rotates at a constant speed. And this is very indicative. If this is on a motor, again, it's just going to go at a constant speed. Even though this problem is very constrained and it's bizarre, they should have a real world example that we can look up that makes this. Because I'm sure there's a mechanism that, I'm sure it's a constant speed right here, but obviously it has to, oscillate back and forth or something, because this thing cannot rotate 360. Okay, hell yeah. So then what they do is just solve for this angular acceleration of b. And again, we know everything because we're going to find the angle at 30. It's a constant angular speed for AB. So again, theta double dot is the angular acceleration of bar AB. It's another way to write it. Hell yeah, it's also omega dot of of AB. But anyway, so that's 0. Sine 30 is 0.5. You know what I mean? And then the angular speed of bar B is -3, but I guess we're going to square it. So yeah. So all of our signs worked. I think that's kind of cool. Beta is that 54.34. Beta double dot. That's what we're solving for. We got it out here. We already solved for the angular speed of beta. That's going to be -2.785 radians. So hell yeah, I guess if you do all that, you get 5.9 radians per second squared. But that's where I'm going to do a second video on that, because I wouldn't trust the differentiation process, because like just the fact that I can come back to this 10 years later or 20 years later and be like, I don't even think anyone taught me the chain rule. You know what I mean? Of differentiation. I don't know where the lack of education was. I don't know if I just was spacing out, but I think you were supposed to get it in calculus class, but those were the classes that were the easiest. Calculus and even differentiation. Those are the classes that are easiest to pass, because you're just given like very doable problems where you're just like, okay, I'm just going to throw the numbers in and get an answer and pass the class. And then you don't realize that when it comes to actually using them, your teachers just like pretend like you know it, and that's insane. Alright, hell yeah. So I'm feeling pretty good about this one. We got the angular acceleration. But yeah, I use an analytical approach. I mean, just in a few words, what I do is I take a very small change in t. It could be a thousandth of a second. That, you know, the smaller the change, the better that you can get. And then so what I'm going to do is I'm going to get a position after that small change, and then I'm going to figure out what the change in angle. I'm going to do that twice. So let's say it's just let's say it's just a hundredth of a second. Cool. This is going to be there, and in another hundredth of a second, it's going to be there. Cool. And then I can actually get all the positions and the angles for beta. So I can get the initial angle for beta, the next angle, and then the next angle. Well, then if I have two different angles, then I know the change in beta. Well, sweet. And then I know the change in time, so I know the change in speed. And then I did that again, so then I can find the next speed. So I can actually find the angular speed of bar BC twice, and those numbers are going to be different. Well, sweet. I'm going to have two different numbers. I can find the change of the speed, which is the angular acceleration. So that's how you do it analytically. And it's pretty simple just to get like an idea. But that's still, in that video, I'm actually going to do a problem where it's just like, well, if you take this all the way in a 360, you could see that maybe this would go back and forth, let's see, I would say like 10 inches. You know, if it goes back and forth 10 inches, but it's not going to be continuous, you know what I mean? It goes this way and comes to a stop, and then goes this way and then comes to a stop. So you're going to have a velocity profile that's more like a triangle instead of just 10 inches per second. The average would be 10 inches per second, but you're going to have 0 here and maybe a max of 20. And if this is kind of right in that 45 degrees, when we go to part 2, hell yeah, look at this. The angular speed of this slider was 25.6. So we could get that just by, you know, just kind of taking the problem to the extremes, getting a feel for it, and just knowing that, hey, and then how do we find those? It's like, well, is because it's going to go from over here to over here. It's going to go from the max this way to the max that way when this does half a revolution. And that's going to do, half a revolution is 3 radians, and we're going to do that in a second. So we're going to do 10 inches per second, you know what I mean? So in 1 second, we're going to travel 10 inches. So that's kind of where I got that average. Well, why isn't the speed 10? Because, well, it's 0 at the ends. You know, if this was rotating in a 360 and this slider was going this way, it would come to a stop. It would slide this way, max speed, and then come this way, come to a stop. Every time it changes position, it definitely comes to a stop. It's going to have its max velocity in the middle, and that's going to have the least amount of acceleration. And then it's going to have the max acceleration at the end. And it'll just be fascinating to run a couple scenarios just to get a feel for, like, hey, even just using the analytical approach just in a couple places to get an idea of what the max acceleration is, and seeing if this is kind of if this is moderate or if this is close to the max. I don't think this would be close to the max at all. All right, hell yeah. Okay, so that was that problem. So now we get on to part 2. Part 2 wants to know the speed of this slider and the acceleration. So that's where we use this equation, and we differentiate with respect to time. So let's see if we can just do this a whole lot faster. Hell yeah. And this video is kind of more just for me. It's like I'm just, as long as I can keep the ball rolling and learn something and talking to a camera, like I'm just, it's all a win for me. Okay, hell yeah. So we're going to differentiate this with respect to time. And I think part of the reason that you can do this is because at any given theta, you know what beta is. And, yep. And I guess if you know what theta... Well, yeah, from the other equation. From the other equation, you know that... Yeah, because the two equations, that's where if you have a triangle, you know what I mean? You have... these two are related by the cosines of these angles. This one is related by the sines. And that's why right off the bat, at 30 degrees, you could find beta. Well, that satisfies this equation. You throw in 30 in that beta, well, hell yeah, you know the position x. So you know all three. So hell yeah. So if you know one, you know all three. So it's kind of fascinating. But I guess we're just taking this and we're differentiating with respect to time. So the first one, we can't differentiate with respect to time. We got to use chain rule. We got to differentiate with respect to theta. But that also means that we're going to have multiplied by d theta dt. So we're going to have a theta dot. Differentiation of cosine. Cosine starts up here and then drops. That's the graph of cosine. Has a 0 angle. So at 0 we need something with 0 that's going to be a sine, but it is in a negative direction. So this is going to be negatives. So it's going to be negative 5 sine theta d theta dt, or negative 5 sine theta theta dot. Got it. Cool. Differentiation with respect to c. So this position c is just that cx. You know what I mean? We also wrote it as that. And the change in the position in this direction is just linear velocity. It's just the velocity of c, velocity of point C in the x direction. There you go. So if this velocity of this slider has, if it has a velocity in the y and a velocity in the x, well, it's constrained, so it only has velocity in the x. And it's just, differentiation is just fascinating to me. I just don't know why I didn't learn it very well. Yeah. I don't know. I blame everyone except myself. No, I'm just kidding. But yeah, it's just fascinating. Okay, so we're going to differentiate with that with respect to time. And that is what we want. We want to take the position. We want to take x, and we want to go dx dt. That is definitionally velocity. That's pretty sweet because it's so that works out. And then when we differentiate this respect to time, again, chain rule again, let's do it a lot faster. We're going to have 8, everything multiplies by 8, but it's going to be, we're going to differentiate this with respect to beta. That's going to be a negative, so we are going to do a plus. So we're going to have 8 sine beta, but we're going to have that d beta dt, which is b dot. Is that a typo? No. Yeah, there's a typo right here. This has got to be b dot. Cool. Well, I'm glad but obviously it's b dot right there, so it's not much of a typo. You know what? I erased it. See, I did Photoshop. There was an erase tool, and I erased that b dot. Hell yeah, but that would have thrown me for a loop, so I'm glad we actually have an idea of what the hell's going on here. And so when you differentiate this equation and you do get that plus 8 sine beta dot. Cool, that's what we get. Then you can rearrange, like, what is this? Well, we want to know the velocity at c. Hell yeah. We know what beta is when theta is 30. So we got 30 and this 54 degrees. We know what beta dot is at 30 because we already solved it from the previous page. So that's kind of fascinating. And if we go back here, hey, look at this. And again, you don't need to do that. You could actually just take this equation for beta dot, and even like we said, even this equation for beta, throw that in there. So you could take this whole equation for beta dot and throw it right into there, and it would just be a function of theta and this angular speed of AB, theta dot. You know what I mean? So that's really fascinating to me. So you can really get, you can take these equations and just make them into, you know, big ol' honking things. But then they're just going to, it's going to be nice because then your inputs are just two things. It's going to be the speed of this, whatever motor's, you know, doing the thing. And then it's going to be whatever angle you want to assess, the velocity at that, or all the velocity and acceleration, angular velocity and acceleration. This is a motor, so you already know its angular acceleration is 0. And that's literally everything that you can come up with this. This has an angular speed that's constant, no angular acceleration. We can find the angular speed and the angular acceleration. And then point C, it's got angular speed and it's got angular acceleration. Hell yeah. And, I mean, if they just chose an angle where this was at its fully lengthened point, you would get a velocity of 0. But you would get a hell of acceleration. Because look at this. The acceleration, even at that point, is 114 inches per second. So, and just going back to here, I think this was a pretty decent change in acceleration. You know what I mean? That looks pretty decent. Okay, hell yeah. Oh, and this is fascinating. We got to go over this. Because this says that this angle is reducing, so this angular, the angular speed of BC is in this counterclockwise direction, and it's 3 radians per second, which if it's right here, here's halfway, draw our circle, means that every second it's going to be going halves. But let's say this thing, well, and then the angular acceleration, and then we have to stick with this negative, because these are the actual, if we're going to clarify this angle as positive, then it's going to be positive from this direction. Hell yeah. Like, this is our baseline of 0 of this angle. And so its speed is going to go this way at 3 radians per second. Now, its acceleration is actually the other way. So we are having a speed this way, but it's hella slowing down. Is that even true? I feel like that's not true or something. That's gonna mess with me. Because I just felt like this was I don't know. Like I figured this was going down and then this was going out, and was coming to a stop. Yes, so if you have an angular speed this way, but it's going to be, if it's going this way at this speed, but then it's actually slowing down, that means the angular acceleration is in the opposite direction. And so, yes, that's where this positive comes from. Hell yeah. So that angular speed that's going this way, so let's do this. Let's say this was negative 3 radians per second, and we had a change in acceleration of positive 3 radians per second. So in 1 second, this thing is going to come to a stop. And let's say it's just huge and very slow, or just let's say it's just very, well, it's hard for this to be 3 radians per second, which gives us all the way over there. That's the only thing about these problems. It's not like linear velocity where you can be like, hey, I want to go for a full second. Things rapidly change. So you wouldn't be able to do that. But you would be able to go for a, let's just go for a 1/10 of a second, because if this was 5, 1, 2, 3, 4, so hell yeah. So you're gonna go from here to there in a 1/10 of a second, and it just means that this is going to be not 6 radians per second, but 0.6. So you're going to have positive 0.6. So this is going to go from negative 3 radians per second to negative 2.4 radians per second. Hell yeah. And then you got that kind of slowing down approach. And then once you analyze at that new angle, obviously these values are going to change. And I imagine this gets jacked the hell up, because you really have to slow this thing down to a stop. So again, I think this is moderate. I do not think this is a high acceleration change. But yeah, I'm just surprised that the slider actually has a pretty good acceleration. But again, you know, I only know how to compare these things when they're in meters per second, because if the acceleration, you know, if the acceleration is 10 meters per second, well, hell yeah, we know that's one gravity, you know, 9.8 or whatever. So, and then we know the human body can only, you know, if this was an amusement park ride, you really can only have 3 Gs. So it'd just be kind of fascinating. But I do not know how to transfer inches, you know, per second to meters per second. But we do, so let's do that. Because that's first chapter of physics. It's just, you know, no one wants to. So you do this, 114 inches per, you know, second squared. And I don't like to do it this way, but we could do 1 second squared. Yeah, let's not, you know what I mean? I think it's just good to get used to just doing inches per second squared, kind of writing it out to the side like that. But we are going to change inches into meters, so we're going to go 1 inch downstairs, cancel that out, upstairs, and that's going to be 25.4 millimeters, and then 1 millimeter is 1,000. Oh hell no, we totally have that opposite. 1,000 millimeters is 1 meter. Hell yeah, we got meters upstairs. And we could have just done this, 1, 2, 3. I need to get better at that, 0.0254. But I don't think I would trust myself. But that is the equivalent, 0.0254 meters per inch. Cool. And then we'd have meters per second squared. Let's do that. So we got 114 times 0.0254. Yeah, we only get an acceleration of 2.89 meters per second squared. So yeah, this thing is going hella slow, but we already said that this thing is going like, you know, like you could move it with your hand. So the acceleration, like obviously, you know, if this was an amusement park ride and you had people in there, hell yeah, this is the limit. 3 meters, no, hell no. This is not even 3 Gs. This is a really slow acceleration. 3 Gs is 30 meters per second squared. Sorry about that. All right, hell yeah. So did we do anything? So we rearranged this equation for change in x of c, which is the velocity in the x direction of point C, and 30 degrees. I erased this. This is d theta. So we have 30 degrees, negative 3 radians per second, 8 sine, 54 degrees, and then we have that negative 2.785. So there you go. The negatives, the 30, the 54, the negative 2.7 radians per second, and we get this speed of 25 inches per second. But it's just fascinating how you can get that just by doing kind of a visual right off the bat. So that was kind of cool. I'll make a video on that. Alright, hell yeah. So, and then we're going to differentiate again. So this is our equation for the velocity. So now we need to go this. We need to go derivative of this equation with respect to t. And it's just kind of interesting that this is the derivative of like cx, of that position with respect to time. And now we're taking the derivative of that, dividing by dt. So hell yeah, that's where you get this d cx dt squared, or just d squared, the position, which they're calling just x of c. Sorry for calling it something different, dt squared. All right, hell yeah. And then so we need to take the derivative of this function. Cool. And we have an addition, so we can take the derivative with respect to time of this side separately compared to this side. So we can factor out the 5, we can factor out the negative, and again, we're taking it with respect to time. So it's the first times the derivative of the second. Sweet. So we're going to have negative sine. Well, I guess they're going to factor out the negative 5. So yeah, let's do that. So we're just going to have sine theta. So this is the first times the derivative of the second. So we're going to have sine theta, theta double dot, plus the second, theta dot, times the derivative of this, but with respect to time. We don't have time in here, so we need to take the chain rule. So we need to take this with respect to theta, but then make sure to multiply by d theta dt, which is another theta dot. So we're going to have theta dot squared, derivative of sine theta. Again, sine goes up. It already starts with a slope of 1. What when 0 is 1? Well, that's cosine. Cosine of 0 is 1. You know what I mean? So it's going to be just cosine theta, theta dot squared. Hell yeah. And then plus... and then obviously we've got to multiply that whole thing by negative 5 once we do that. Come over here, we're going to factor out an 8. Oh man, I don't know why they... this negative is everywhere? Does this negative factor through the whole thing? I guess so. Yeah, that's a bummer. So again, we're going to factor out another negative 8. Okay. And then we're going to take the first times the derivative of the second, sine beta, beta double dot. Okay, hell yeah. And then same thing. We're going to take the second, that beta dot, we're going to put that first, times the derivative of this with respect to time. We can't do that. We got to take it with respect to beta, but then do the chain rule. So we take derivative of sine beta with respect to beta times derivative of beta dt, which is beta dot. So we're going to have another beta dot. That's where we get the beta dot squared. Derivative of sine, again, sine goes up like this, and that's going to have a slope of 1. What's 1 when beta is 0? That's cosine. So we're going to have cosine beta, beta dot squared. Hell yeah. And there you go. And then just make sure you got that negative 8. This negative factor through, that sucks. I hate negatives. No, it's just kind of fun to say, like, you at least hate one thing. But no, they trip you up. Like, there's no more mistakes ever. Yeah, a lot of mistakes get made. Negatives. All right, hell yeah. So you have, did we do it? Where the hell, shouldn't this be x double dot if we went through all that work? That's insane. Like, where did we go from x of c dot and then just differentiate the hell out of it? I'll have to check that. That's an error in the book. They didn't do a double dot there. You know what I mean? That's just lazy, and that's a huge error. That's where just even textbooks, no one even can critique them because no one knows what the hell's going on. You know what I mean? So, but anyway, so we know what angle at 30. And again, look at this. We have theta double dot. That's the angle, well, not this one, but that's the angular acceleration of bar AB. It doesn't have angular acceleration. It's constant speed. It's like a motor spin in this one. You know what I mean? So that's always kind of problems where you're like, hey, this is a constant speed. Just think a motor is spinning that one. But this one can do all sorts of things. And then so we have this beta double dot. Well, we had an equation for that. And this, you know, this was 0, but, and then beta could be in terms of theta anyway. And then beta dot, again, can be in terms of theta, beta, and then beta can be in terms of theta. And then, so it's just theta and that angular speed of the original. So yeah, you can make these monster equations where it's just, where this whole thing, the acceleration of point C, so we're going to do that, x of double dot, or just the acceleration of point C in the x direction, that's really all you're doing, is just a function of well, mainly just theta, because theta dot, or omega of AB, is a constant and it's given. You know what I mean? So it's not even, that's not even, you know, I mean, it's a function of that, but that's a constant. But I mean, it's a function of it in terms of you can change that variable. But yeah, these are the only, you could get the acceleration of this point with just in the inputs of like, hey, how fast is your motor spinning, and then what is this angle going to be between 360 degrees. All right, hell yeah. Man, this is brutal, but this is so interesting to do. I'm glad I'm doing this. And it's just more for myself. And, you know, I always say, like, oh, we'll get better. But I just need, I don't know, for whatever reason, I need to do this stuff, you know, into a camera because I can just learn so much. Because I'll totally be totally frank and obvious of just crap that I do not know. But it'll point it out to me. It's just like, yeah, I do. I want to know everything about the letter usage of differentiation. I think it's messed. You know what I mean? And I think just a lot of simpler problems could totally spell out where a lot of this stuff comes from. But anyway, hell yeah. So we did it. So we have the acceleration of that point. Again, this is 0. This is the input angle. This is the input angular speed of AB. This, we just said, is a huge equation that's still a function of theta and theta dot. Just like this whole thing's a function of theta and theta dot. Cool. Beta is a function of theta, and yeah, for sure this is just a function of theta and double. Well, let's look at this. Yeah. And this is just a function of beta dot, which is just a function of theta and theta dot. And then everything else is the same. So yeah, that is kind of cool. And booyah. So there's the angular acceleration. But again, what you're doing is you're just getting values for one point, which is kind of nonsensical because you don't get an idea of how this whole thing, like maybe there's an acceleration that's too high that's just going to, like when you actually do the stress analysis of this member, maybe you didn't design it. Maybe because if you have an acceleration, this is a cool way to end it. You do have F equals ma. So cool, you got a number for acceleration of this. You got a number for the angular acceleration. You know, all those things are going to, well, is this true? Oh, this is cool, you know what I mean? Because if this thing is spinning and then, or having an angular, if something is spinning and having an angular acceleration, it comes to an abrupt stop. Things that come to an abrupt stop, you know what I mean, and then like shift gears back and forth. Like one thing that comes to an abrupt stop that does damage itself is a saw stop. You know, you have a saw, it comes to an abrupt stop. The acceleration is so crazy that it will rip. Like these little, the tips, the carbide tips will just break off. You know what I mean? And that is the same thing as you just taking the carbide tip of that saw, putting a force on it, like pulling it with like a, you know what I mean? Like welding a rod to it and then pulling on it until it breaks. That same force that's required to break that off. And it might only be 200 pounds, but still, the fact that you can just stop a disc that has mass with an acceleration, and this is angular acceleration. Your angular acceleration is so huge, and then you have a radius arm to the extremes, you're not going to have any force in the middle. Same thing here. If this thing has an angular acceleration, well, hell yeah, the ends are what's wanting to like fly off. So that is kind of that's a good way to end it. You do, like if you just have a member that's just spinning real fast, only the ends are suspect to like, you know, like ripping themselves off. The center doesn't really feel much at all. So, hell yeah. But yeah, getting the number on acceleration and then probably angular acceleration, I just don't know a whole lot of how to assess that. Yeah, I don't know. Because it seems like even if this is kind of in line, and that's when it's, you know, coming to a dead stop, I'm sure that puts a lot of force, tension force on that. And not necessarily due to it spinning its ends off like a saw stop, but just actually coming to a dead stop and then coming back probably tensions that member, and so you need to know the forces that you can handle in whatever you design that. And then F equals ma kind of spells that out. Yeah, and I mean, F equals ma spells it out. Like, let's say these are just like massless rods, and then here's all your mass, and then this mass is coming to a stop, and that's kind of like what you're like the force needed to bring this to a stop is the force that's these things would be like in tension. They're actually the only thing that's holding this just from just like ripping itself off and then just going down, you know what I mean, no longer being part of the system, because you put a mass in motion and then due to geometry you're quickly bringing it to a dead stop. And the only way you can do that is by putting a force on it. Yeah, so this is a good way to end it. So you do have a mass, you have a hell of a velocity because it's traveling that way. At just right here, it actually comes to a dead stop. And the only way to get a mass to change its velocity is to apply a force on it. That's why I kind of brought it back to F equals ma. And yeah, that is something that I would actually do just with... and then these equations, like even though they're monstrous, these are exact equations. They're just hard to put anywhere. I mean, I think graphing calculators need to get updated, 21st century, because, yeah, the second you input an equation, man, you should be able to store that thing. You know, these things are just really, really mediocre. You know what I mean? Just when it comes to an analysis of these equations, no one's actually putting them in. Like even in graphing calculus, it's really hard to actually, trace the, to get an idea of what your acceleration. It's not too hard, but I'm just saying when it comes to the analysis, sometimes just knowing that, hey, when this thing's at, like finding the extremes from a perspective of just kind of knowing where those accelerations, those high accelerations are, and then just doing a numerical analysis, just like, hey, let's just get it out here, change our time by a... Alright, hell yeah. So we're running out of juice, but I guess what the hell were we even talking about? Just F equals ma, just kind of doing a numerical analysis, knowing where the maximum accelerations are. But if you do graph them, hell yeah, you're like, this is the acceleration. Where this graph is at a maximum, that whatever theta generates that maximum, because this basically is a function of theta. Everything else is constant. You're going to have a constant speed. This is going to be your acceleration, which is 0, because you have a constant speed. So this is 0, this is constant. And this is a function of the angle again and the constant speed. So we have, angle, 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 angle. You know what I mean? And then constant speed, constant speed, constant speed. All those have constant speeds. But, yeah, so you're going to have, at some point, you're going to have a theta that is going to be the max where... this is, so whatever angle that is that position is going to be, anyway, and that's going to give you the acceleration. So you're going to get the acceleration of c, and that can help you determine, what the forces are going to be generating, and then so you can kind of size your members. Anyway, enough said on that. Man, this was tricky for me, but I'm just glad I learned the chain rule. I didn't know how useful it is. I didn't know how bad I was at differentiating. I honestly don't really even know, the one thing that other problems have is hey, you have this 4 inches. This could just be a height h. Another variable. See how you have theta, beta? There's no reason where this could just be height h. So when you differentiate, when you do dh dt, guess what? At any given time, this is a constant. So if you have an equation of height as a function of time is just going to be 4 inches. That is the equation. It's not a function. It's not a function of theta. It's not a function of beta. You could say it's a function of time to the 0. Cool. You know what I mean? It's just, you know, there you go. And it could be a function of all those to the 0. But when you differentiate them, you know, even if it's 4 inches to the theta to the 0, and you're differentiating with respect to theta, or even doing chain rule where you have d theta and then d theta dt, where you have theta dot. Well, the differentiation of 4 is 0, so 0 times that speed of negative 3 radians per second is 0. So it's just kind of fascinating. I definitely teach that. Sorry I just scribbled that in at the last minute, but it just kind of gives me some ideas. Yeah, and it's just fascinating that, like, all my videos, it's like, man, and I could have spent 4 hours on this one. I'm just glad it was a pretty good pace for me, and I think I learned a lot. But yeah, it's all the same. It's like, man, it's like using everything you know all at once. And it's just kind of fascinating. I think that's pretty neat. Alright, Helly, I'm done with this. Holy Toledo. So thanks for joining me, and guess what? That's a video.